will follow basically the same, the footstep of what Miguel Machuquero did in his presentation. In the first part, I will give you a survey of what we have been doing in the last years to, as far as electrostatic simulations are concerned, mostly in the field of biomolecular recognition, and the final part, what we are actually starting and to do in this respect, pointing to the roundtable of this afternoon. So basically, so when I first went into, I am an electronic engineer by training, so I went into Berihonix lab more than 20 years ago, and that was kind of a shock. But one of the things that I learned is that so electrostatics and hydrophobicity are the main determinants of molecular recognition and binding. So after several years, I think we finally managed to set up a number of ways of exploit I would say the magic functional form of electrostatics during simulations in order to actually help us understanding much better how biomolecular processes are behaving, and this can be of great help in for example in the field of drug design. So I will briefly go through 3 of these examples. So all of them somehow use in one way or another an electrostatic bias. So before doing this, I have to mention about NanoShaper, who has been instrumental in all of our approaches, actually. So the NanoShaper tool was created in 2013 with the aim of complementing Poisson-Boltzmann solvers in order to have a better and more reliable mapping of the dielectric constant in and out of a protein. Molecular structure, and also to understand what's going on in terms of the fact that apparently the surface area of the solvent extruded surface was not continuous with respect to the position of the atom. In some cases where you have a small movement of the atom, nearby atoms, the probe can actually get in or get out, and you have actually a jump. And we were able, thanks to the NanoShaper analysis, to figure out that actually the area is continuous if you also consider the cavities which are inside, with very small cavities that actually join the external crevices when the atoms get a little bit farther away. So we did this work, and we ended up with a tool that is now, I'm proud to say, is used by many people, many colleagues here. I'm very happy that this is occurring. We managed to deal with large systems. We also were able to observe that pairing this with Poisson-Boltzmann solver, in this case it was Delphi, enables you to actually, let's see, to actually get a much more stable energy estimate with respect to the resolution of the grid we are using, which allows to have a lower resolution without sacrificing the accuracy. So this actually proves that a more accurate surface estimate, together with the tricks that Delphi is using in order to get the energy from the surface, it is really a good combination in order to improve the quality of the results. And we also managed to convince people from BMD, especially John Stone, to include NanoShaper as a plugin, as a possibility to build the surfaces in BMD, and he was convinced by the fact that it was able to build the surfaces for very large and complex systems like Fatrin and viruses like that are shown here. That was not possible with the other tools at the time available. So I can say that. So now NanoShaper is a bit old and can give some headache to compile on your system. So we are trying to renew it with the collaboration of Sergio De Kerchi, who is no longer in my group. He has his own team. So I think, I hope that soon there will be an MPI version coming and more modern and easier to use. So by means of NanoShape, we were able to build surfaces to have a better visualization tool, to improve the Poisson-Boltzmann calculation, to identify potential pockets, and to use this to analyze their evolution during molecular dynamic simulation by means of the Pocketron, which relies on NanoShaper for pocket definition, and very recently also to get a better characterization of potential binding sites by combining the NanoShaper surface building tool with some machine learning in order to try to get a better estimate of which putative pocket is, it could be ligandable or not. So going back to when I was saying that with electrostatics you can observe very many interesting phenomena, you can accelerate them. So I will briefly show you a few examples of this. This is what we call the MD binding approach. I will go very quick. So by means of NanoShaper, you identify the pockets, then you can also identify the regions, the exit of the pockets. You can place ligands a little bit out of their entrance. You can run a simulation where you apply a contrived electrostatic attraction between all the heavy atoms of the ligand and the heavy atoms of the binding site. So the protocol is not as easy as I'm saying now. It's a bit more complicated, but the basic idea is to combine electrostatic field lines with, let's say, a limit on the energy you are pumping into your system while you are doing the simulation. So this is not in contrast to what Lauren was saying this morning, talking about the milestoning. As many other enhanced assembly techniques, they need to have a good approximation of the reaction coordinate they want to study in order to get a reliable, for example, free energy. In this application, we try to overcome this problem. We are not looking at this stage for the free energy of binding. We are saying, let's say that we have an apo structure. We don't know we want to do something like docking, but in a dynamical sense. If the pocket is closed and you are pushing, regardless which is the functional form, you will inject too much energy into your system. You will not get any physically sound trajectory. So in this case, we do several replicas, and we are kind enough to keep the total amount of force we are applying to the ligand and to the binding site always limited, so that if the ligand doesn't enter a period, we will discard the trajectory. But in some case, the ligand enters, and I will show you that with 20 replicas, we always manage to get at least one successful trajectory. And when you do this, and when you turn off the bias, actually, as soon as you overcome the supposed transition state, let's say that the region where the energetically the ligand has to climb some energetic barrier, actually what we get is a really good sampling of the states, conformational states nearby the bound one, and we were able to compare them with the crystal, with getting very good agreement, also starting from apo structures. I will not go into the details because I already described them in previous presentations. The results, I think they are pretty interesting. So we applied this to drugs or putative drugs, really used in some of them are blockbuster in the pharmaceutical companies. And what is interesting to see is that in terms of computational time, there is a huge saving, because we managed to get a bound pose below 2 Armstrong RMSD with respect to the crystal, with, let's say, 400 nanoseconds aggregate, which can be independently parallelized in 20 replicas. If we compare the few cases where we have a brute force approach, maybe because it was done in the D-Show research with the Anton supercomputer, or because of very many GPUs applied to this, we can say that we were able, for example, to study the cases that I showed you before was a SARC kinase against PP1. That was done by also by the D-Show group, and they found one binding event, 3 binding events with 2 ligands into the simulation, but the mean time for binding was 117 microseconds, if I remember correctly. So this is something that can hardly be reached even by present computational resources. So, but you can do some tricks and get very similar results, which I think is very interesting from this point of view. So I switch. I try to reverse the application. So hydrophobicity, of course, is more complex than electrostatics. It's not pairwise, something simply pairwise interaction. But we can do, if you want, we can mimic the effect of hydrophobicity by tuning hydration of given regions. So there are tons of papers talking about hydrophobicity, and I would broadly classify them in 2 different classes. One is more from the physical point of view, when you have an ideal or reduced system, when you can really switch analogically, I would say, the hydrophobicity, and then you study the dynamics and the probability of binding of spherical ligand, for example. And then there are these more chemical inspired, where they actually look at the full atomic detail, and they consider the energy and the propensity of water molecules to get stuck into some binding site, for example, and see how can be convenient for a ligand to displace a water molecule or not. But you cannot really condense this individual water propension to something like hydrophobicity. So we try to merge these 2 different approaches by simply using, again, electrostatics. So we apply, again, a contrived bias that slightly increase the repulsion or increase the attraction of a group of atoms of your system towards the nearby water molecules. So you are not changing the hydrophobicity or hydrophilicity, but you are forcing a different value of the hydration. And we were actually able, again, by studying kinase, the SARC kinase, to get an acceleration of the binding process, not as significant, not as marked as in the previous approach. But still, if we slightly dehydrate the ligand and the binding site, we are actually increasing the chances to observe a binding process in a molecular dynamics simulation. And if your protocol is such that when the hydration is more than our aim, then you are actually slightly repelling water molecules. But after the hydration is our task, which is, in this case, it was 80%, after that, there is no more bias. So also in this case, once the ligand kind of enters the binding site, it becomes a plain molecular dynamics, and you can get statistics out of it. So we were able not just to use this to find within 70 replicas one that went to the to a bound pose, which was below 1 Armstrong RMSD from the crystal one. But we actually got several interesting qualitative, in some cases also quantitative information out of it. So the first question we posed ourselves was, is this trick really mimicking hydrophobicity? So it's hard to answer this question, but one thing that was always discussed in these many papers from the physical standpoint concerning the hydrophobicity of surfaces was that the difference in hydration of the hydrophobic surface with respect to an hydrophilic one is in the fluctuations of water nearby. So we wanted to see whether we were observing the same increase of fluctuation while reducing the hydration of our pocket, and this is what actually we observed. So at least from this point of view, we can say that we are convincing water to act as our molecule, which can be a real drug target or a real protein, slightly less hydrophilic as it is, without making any mutation, for example. Also because mutation, you cannot gradually mutate. You either, so if you make a mutation, then you get all the properties of the mutated residues. While here we can slightly switch off the interaction, the propensity to interact with water. And I will not get into many details, but this helped us figuring out the importance of a salt bridge that was present in the binding site of the SAR. And in many other, as we did some bioinformatic analysis in many kinases. And what was interesting is that, so you imagine intuitively that when you want to push binding, you would like to get the binding site empty. So you want to kick off water out of the binding site because the ligand must enter. But if there are, like in this case, salt bridges inside the binding site, if you are actually dehydrating the binding site, you are strengthening the salt bridge. So you are actually keeping the site more rigid. And in this case, you are reducing the probability of that salt bridge to break, and you are reducing, for example, the probability that the ligand can enter. And this is not just something that is artificially induced by the simulation. Actually, this is what a protein can do when it gets resistant to cancer. So there is a very well-known from people who are working in the cancer field. We did this with as a collaboration with Bisana Lazzicani, that at the time was at the ICR in London. So there is a well-known mutation, which is 338 to thionin, that is a resistance mutation after the cancer is treated with some kinase inhibitor. If you look at this, the effect of this mutation is actually that makes the side a little bit more hydrophobic. And by making this, we did some analysis of plain ND of the hydration of the site in the two cases, and also of the probability of breaking of that salt bridge. And what we observed actually was that lower hydration and more and less propensity of the salt bridge to break. So this actually was something that we were not coming from this field, so it was deriving just from our analysis made by forcing the dehydration of the site. Finally, and I'm happy that the previous speaker already mentioned about the cryptic pockets. So there are several attempts to identify cryptic pockets in molecular dynamics. So cryptic pockets, by definition, are not present or are unlikely to be present in crystals. They are also unlikely to be observed in plain molecular dynamics because most of the time they are closed. And there are people who are trying to do mixed solvent molecular dynamic simulation, where they add some usually hydrophobic moieties in the simulation in order to convince some pocket to open. But again, this brings some complication. Running a mixed solvent molecular dynamic simulation is not trivial. But in our case, it is really, I would say trivial, but almost it is. You can make the protein surface slightly more hydrophilic. When I say more hydrophilic, I mean you add a propensity to be more attractive for water molecules. And in this case, you are convincing your protein to open regions that potential encrypted pockets that were usually closed. And the nice thing of this approach is that you can do very gradually. You don't need you don't have to force your system too much. The application we tried was, so during COVID, there was this this paper from a group of Bristol where they actually crystallized the spike, the RBD of the spike protein with a fatty acid in a binding site that was not known beforehand, and they knew only because they crystallized with this most hydrophobic molecule. So we want to see whether we would have been able to find the very same pocket without the fatty acid, just by artificially increasing the hydrophilicity of the surface of the RBD. And this is what we actually obtained by simply bringing the local hydration from the 100% that was measured in a plain molecular dynamics before to the 110%. So by slightly increasing the propensity of the surface to attract, to interact with water molecules, you of course convince many regions to be more exposed. And of course, as it was in the previous case, you get many answers, not just one. So then you have to figure out among the little sites that open which one can be promising for being functional and ligandable. But this is anyway a quite easy way to have some candidates to test with. So to finish let's say the survey of the past, so by tweaking electrostatics, you can observe very many things in terms of related to biomolecular processing, especially protein ligand recognition and a similar phenomena. I would like also to stress the fact that none of those biases can be considered per se alone a good collective variable in the sense I was saying before. So if you plan to do some enhanced sampling in order to get some free energy, then you have to know to have a very good approximation of the reaction coordinate for your system. And there is no general definition of it. It very much depends on your specific system. So this is a way to stimulate the occurrence of some interesting phenomenon when you don't have the knowledge of that reaction coordinate. And for a new system, you usually don't. So this is something that I think is interesting when you have a new target for which the relevant degrees of freedom are not known. Okay, so let's now switch to my friend continuum electrostatics. So we actually at some point wanted to start from the beginning, and considering the fact that when we do our work, we have, and especially now that these structures from very large systems are coming and processes. So there is a range where you can apply numerical approaches, for example, within Poisson-Boltzmann framework, and there are other distance or scale ranges where you can apply analytical approximations like the Biomolecular, and there is some intermediate regions where the approximation are too rough, but the numerical approaches are unfeasible because of computational costs. So can we improve the analytical approximation in such a way that we can eliminate this intermediate region? And so we can actually combine directly the join domains where you can apply numerical approaches and those where you can apply analytical approximation. And with this in mind, I asked a postdoc and applied mathematician, we see here, Sergi, to try to improve what was known about the analytical interaction between charged systems in the linearized Poisson-Boltzmann framework. And I was actually astonished to realize that despite I was thinking that the interaction of two spheres within the biomolecular approximation was a closed topic, but that was not the case. So actually, I realized that an analytical definition and expression for two spheres interacting in not overlapping, just interacting in the linearized Poisson-Boltzmann framework was not available. And so after some time and a lot of work of Sergi, we came up actually with a nice expression, maybe not nice to see, but a nice expression for the energy and the potential within the spheres and outside the spheres. And the nice thing of it is that you can actually separate, like it's not a real Taylor expansion, but it is an expansion where the first term is in the biomolecular form. So it is the known, what you would expect in the biomolecular expression. Then you have powers of it. So you can actually decide where to stop and the accuracy that you want to get. And for every of these orders, you have a description which is analytical. It can be very bad, but very bad looking, but you can code it and calculate pretty quickly. And this is useful because it allows to benchmark all the other approximations that have been done or that are also done, for example, in the colloidal field. Because in many cases, some approximation have been done, but there was no ground truth to compare them against. So this is something that we are going to show that we are going to use this also for our more numerical applications. So now Sergi is about to prepare the counterpart when you have many spheres, not just two. So in order to get to allow for the possibility to have a good estimate of the potential and the energy, and you can analytically separate, for example, the ionic contribution from the polarization contribution from the Coulombic contribution in a very neat way. So and that was back in 2021, and more recently, the approach was ported to let's say arbitrary shape particles. Of course, then it cannot be any longer that analytical, but still the principle is to be able to have some expansion that you can truncate at the level of accuracy that you need in order to perform your simulations. And we compared our results with some specific geometric forms for which we can compare against Delphi, because the old Delphi had the possibility to have geometrical objects, so we could do this comparison, getting very good agreement. And we also observed something which is interesting. So at that time, we weren't able to include the molecular surfaces into the analytical code of Sergi. Now we can. I will talk a little bit later, but we can put inside our objects the charges whenever we want, wherever we want. So we want to see something that we tried at the very beginning with NanoShaper and Delphi, to do the potential of mean force that you get when you approach to side chains. In that case, since it is a grid-based approach, it is impossible to avoid the oscillation you get when you are jumping from one grid side from one grid cube to another one. And that was especially critical in that case when we use the charm force field, because in the charm force field there are polar hydrogens which have a 0.3 radius, I think. And so in that case, in order, you even if you use a very high resolution, which is not done, by the way, in that also in that case, also in case you use a very high resolution, you get oscillations in the energy at any time, and you cannot avoid, you cannot preserve the mutual position between your system and the grid if you want to approach two things. Either you preserve on one or you preserve on the other, but if they change the distance, you cannot preserve for both. So we did this with our approach. This is what you actually see. Our approach is gridless. So these oscillations are lacking by definition. So what's next? So when I said arbitrary shape, so then you may ask, okay, so can this arbitrary shape be a molecular surface, Connolly surface? In principle, it could, but then we are realizing that the roughness and the complexity of the surface need a large number of coefficients in order to get a good accuracy. And beyond this, this leads to a bad conditioning. So there are problems that needs to be solved before we can say this can be a viable alternative to a regular traditional Poisson-Boltzmann solver. But we'll see if we manage to overcome this problem, or if we have to stick with this, which still is interesting, because, for example, we could derive rigid body forces to be put in Brownian dynamics code when the system are a little bit far away. So this can be already much more, can provide a big advantage because it is gridless. So the fact that two things are here or there from the computational point of view is completely irrelevant. So this is interesting development. As I said, many bodies, their capability to consider more than two objects is on its way. We are all apply some of it to the nonlinear formulation, basically by the concept of replacing a linear particle in a nonlinear solvent with a nonlinear particle in a linear solvent. That's because the nonlinearity is localized around the particle. So we could say whether we can, we could see whether we can find some kind of nonlinear description of the polarization inside that macroscopic particle. But then once we have done this, the solvent outside is still can still be described by the linearized Poisson-Boltzmann. So this is basically work in progress. So that was from the, let's say, analytical side. Let's now go to the numerical side. So again, when I went to Barry's lab, one of the things that that was taught to me, so if any simulation we are doing is based on models, and models are wrong, that if they are fast, they provide fast some answer that others can use. If your results take a month to be obtained, even if they are, they will always be wrong. So let that be as fast as possible, let's say. In this case, so we decided to follow two different paths. One is the acceleration of the linear Poisson-Boltzmann solution. Of course, prioritizing some features, some aspects. And this I am looking forward to the roundtable of this afternoon. Treat large system is one of them because, as I said, cryo-electron microscopy is providing so many large structures that we need to have some tools able to deal with them. And on the other side, to see whether we can do something better than the traditional nonlinear Poisson-Boltzmann in order to see whether we can describe different ions to better describe some of the systems that Thomas was talking yesterday, to reproduce the optimizer series, for example. So concerning the first part, this is the content of the poster that Vincenzo, who is a PhD student in my group nowadays, is doing. So we borrowed actually already existing linear system solver, highly parallel library in collaboration with mathematical engineering from the Polytechnic of Milan, especially the Professor Carlo De Falco. So this is finite element orthogonal grid, which can be refined upon desire, let's say. So we in this case, anytime you have a cell, you think you need a better resolution, it's divided into octant. You can then either refine or de-refine. So you can simplify your mesh when you are getting closer to your boundaries, the boundaries of the box, I mean, because you don't need to have a very high, a very refined grid in that region. And while you can refine it where you are interested in, either because there is the complex geometry, or because it's where you want to estimate your pKa or something like this. So the aim is the rule of the game is to get a better accuracy without increasing too much the number of unknown that we are solving, of the system we are solving. And we compared, as you can see in this plot, the results around the surface against what is provided by Delphi, and we get a very good agreement. We interfaced this code with NanoShaper. So for the molecular surface, everything is fine. We then analyzed the scaling with respect to the number of processors by using different solving approaches. One is a direct method, and the other one uses a number of iterative methods. And we are, let's say, trying to get our best option among all of them. There are some advantages of direct methods. For example, if you want to keep the same surface, change the charges. For example, you can just change the right-hand side, and while your matrix is still the same. This is very convenient from the practical point of view. But since now we have a tool that relatively easily allows for have a different solution in different regions, then we could try to see whether we can leverage it. And one interesting thing is the role of boundary conditions. So the boundary condition that I always have been using with Delphi were called Coulombic, which actually more accurately would have be called the Biomolecular, so the exponential divided distance. But this, if you have a large system, this goes as the product of a number of charges times the number of tiles you have on your boundary. So in some large case, assigning the boundary conditions may take as long as the solution of the system. This is Delphi, all Delphi, and serial one, so not parallelized. I understand that there are, as we were discussing with Robert last dinner, there are many ways you can accelerate this. Still, it is remarkably time-consuming. So, what are the alternatives? There are two. So the natural alternatives is zero potential at infinite distance. So infinite, of course, we cannot reach. Then we can use Neumann. So you can say, well, if the potential has to go to zero, also the field has to go to zero, but the field will go to zero faster. So if you need a huge box to apply Dirichlet boundary condition, you will need a less huge box to apply Neumann homogeneous conditions. And this would be, however, exact in the sense of the physical meaning. Are Coulombic approximation as exact as those? Actually, no, although they are very good approximations. So I told you before that we were able to express the energy and the potential of a system composed by many spheres in a way that is proportional to the Debye-Huckel terms, the square of the Debye-Huckel, third power, and so on. So you would expect that the Coulombic expression is an asymptotic truncation of it, and gives you the first term, the one that is the coefficient of the first order Debye-Huckel term, which is not the case. And actually, and this is, I'm trying to explain, to find an easy explanation for this. So with the same machinery, which is basically second green identity, that is used to get boundary element expressions, you can say that the potential in solution can be written as the sum of two terms. One is, as you see here, this you can think of it as a charge at the surface. So gamma is the surface of your protein, which is screened. So you have a number of charges, which not necessarily are polarization charge, but they are located on the surface, plus a number of screened dipoles. Again, you have dipoles, and you already have you again have the exponential decay. So let's say that the dipoles decay first, so we can neglect this term. We concentrate on this. So if you were expecting to have the first order term, you would need to have a number of charges spread over the molecular surface, which is not what you do when you do Coulombic. You couldn't do this because you don't know the amount of the charges. These charges are known only after you solve Poisson-Boltzmann, so they could not be used as a boundary conditions before the solution. So Coulombic approximation is not the first term, is an approximation of the first term, while Neumann and Dirichlet would be exact solution, but maybe they will need a larger extent. So we want to have a quantification of this. So we use the free spheres. As I said, we are using the machinery that Sergei provided us with, and we ask ourselves two things. So if I put a threshold on the absolute error, like 10 to the minus 5, how big should be how small should be the pair field of the system in order for these three boundary conditions to be fulfilled, to fulfill this requirement? So you would, for Coulombic, you would need a percentage filling of slightly less than 11, for homogeneous Neumann 9.6, and homogeneous Dirichlet 7.9. And the other way around, since we use, at least I use usually 80% of filling, how much are the absolute error in the case of these three spheres? So I get, so these could be atoms. So the charges and radii are very similar to what we use in our proteins. So I would get, with 8% of per fill, roughly 2 millivolts of absolute error in the case of Coulombic. I would have 1.04 for the field in the case for the field, and 2.69 for the potential. So while I have to say that it is quite known that the energy estimate is pretty robust with the also let's say inaccurate boundary conditions, the potential is more sensitive. So in principle, we should use a smaller pair field that we use traditionally, but that would be more costly. However, if we can afford having a larger box while not increasing so much the number of unknowns, so the computational complexity, we could use Neumann homogeneous boundary conditions, which are actually for free in the case of finite element, and you will skip the problem of assigned boundary conditions. Let's now turn to the second part, the nonlinear Poisson-Boltzmann. So we discussed a few days ago about the role of the nonlinearity and how it acts. So just to, this is probably known to all of you, but just to say something to the youngest people among us. So there is only one analytical case where you can solve both the linear and the nonlinear, and this is the planar case. And in the case of the planar case, if you see compare the results, what you see is that what you can interpret out of it is that the nonlinearity is providing a very strong, exponentially strong reaction to the local electric field, so that in the vicinity of your molecule, the potential decreases much faster than in the case of the linearized one. Then, when the potential go around, let's say 1, the normalized potential, 25 millivolts, basically, then the behavior of linearized and nonlinear becomes exactly the same. So this very strong reaction has two problems, at least. One is that one is physical, in the sense that the corresponding number of counter ions can be so large that physically couldn't fit in that place. And the other is numerical, in the sense that if you have some charge which is very close to the solvent, you might end up having a very, very high potential and a very, very high reaction, which is exponential, and you may end up not converging, which is the case. We did a number of calculations on the nucleosome particles along a molecular dynamics simulation, and in 30% out of them, we didn't manage to get convergence for the potential. So what can we do? So let's start from the right physics, if we manage, and then we see whether this will improve also the computation. So I found this work quite hidden in the literature, I would say, that I liked a lot from the point of view of modeling of the system. So basically, they start similarly. You could start in a similar way for deriving Poisson-Boltzmann equation. So you have a functional, which is the energy of your system. You have the electrostatic part. Then you say I have ions in my solution. They usually are hydrated. There are also experimental ways to estimate the size of this hydrated ion. And this hydrated ion has a dielectric constant, which is not that of water, it's smaller. Then there is this Brueggemann approach, which is homogenization approach, where basically you say, if I have a huge solvent with spherical particles, and these spherical particles have a different dielectric constant from the matrix, in our case, water, what is the, I don't like to say average, that's the equivalent dielectric constant of your mixed solvent. So it is a combination, again, not an average, but a combination of the dielectric constant of the matrix and the inclusions, which is done in material science, for example. And of course, you can set the concentration of the inclusion, and you get the equivalent dielectric constant. So this is conceptually is very simple, mathematically a bit less, but conceptually is very simple. So in this case, if you manage to describe the solvent in this way, you say, if I have a concentration of ions, I will have also that dielectric constant, which will be the mixture of the dielectric constant of water and the dielectric constant of the ion. This will change according to the concentration, which brings, of course, complication in the calculation, but it makes very much sense. And I like this because this will imply that you have a lower dielectric constant nearby the surface, then the potential is less screened, then you might have your territorially bound ions more bound, more strongly bound, because they are less, the interaction is less screened. So I like this from several points of views. Then there is the other point, which is already part of many size modified Poisson-Boltzmann. Okay, you have still a description in terms of concentrations, but your concentration cannot get beyond some threshold, because then you have overlap between your hydrated ions and water. And then thus you have the usual chemical potential formalism. So we are trying to implement this possibly in a clever and not too slow way. This is possibly has to be said in capital letters. And to evaluate the computational cost. But I would be really curious to see whether by using this formulation, we would be able to reproduce the Hofmeister series and then all the other, many of the other quantities that experimentalists are actually providing us with. So, in conclusion, I think there is still space for improvements in the continuum electrostatic solid field. Input from you is very important because there are many paths that can be followed, but only some of them may be really useful to the community. And I really think that in order to get some interesting progress, we need to put who has the problem side by side with who might have the solution to the problem in order to see whether they can talk and find the best combination. And I'm looking forward to a roundtable. Then let me thank Sergi, Vincenzo, Patrizio, who is helping us with the theoretical description of solutions, Professor Carlo De Falco from Polytechnic of Milan, which is helping us with the more numerical parts, and Sergio, who is taking care of the nanoshaper development. And thank you for your attention.
Thank you. I have a question about Cartesian adaptive grid you mentioned. You emphasized basically benefit of that one in terms of computational efficiency, right? I think probably there will be another advantage, which is basically smaller output size. Is that right? I mean, total number of grid points will be smaller, and because of that, the output file will become smaller. And maybe that's not a huge advantage, but for example, when we do Poisson-Boltzmann calculations using Delphi or APPS, sometimes we do such calculations for hundreds or maybe thousands of structures of IDP, I mean intrinsically disordered proteins, for example. And then the output files are huge for our small computer, like just regular PC or Mac. You know, we experimentalists do not have access to fancy large-scale computer resources, right? Yeah, faster calculations and also smaller output are going to be really useful for for us experimentalists. I'm wondering if that Cartesian adaptive grids can be also applied for nonlinear Poisson-Boltzmann.
Yeah, absolutely. So let me first say that, for example, I don't know about IPBS, but I know for Delphi, you can actually, so of course, if you have a uniform grid, you have lots of information on regions where you don't care. And this is a waste of space, disk space. But in Delphi, if you are interested in the potential at given points, you can only get the results on those points. You can avoid dumping all the grid potential. So there is a way, even with Delphi. I must say
but we need be difficult for white space.
Okay, then if you need the information for a white space, you probably will need a lot of points also, regardless the approach you are using. But if you are interested in specific regions with Delphi, you can already save some space. I must say it would be difficult to overcome the capabilities of Delphi in the future. Concerning, sorry, the other question was the
applicability to nonlinear.
Nonlinear, yes, absolutely. Actually, all of those machinery come from the finite element world, and they are also used for nonlinear equations. They are also able to refine automatically, finding out not because I say them, but they realize where there is the need of a more refined grid automatically, because when you are dealing with nonlinear equations, it may be not so intuitive where you need a finer grid. In our case, we know we have already a very good very well educated guess. But in some cases, if you have Navier-Stokes, for example, you don't have such an educated guess, not necessarily at least. So I say yes, absolutely, and we will be using all the same machinery for the implementation of the nonlinear. It's difficult. It is technically difficult.
Thank you.
Thanks. Very nice talk. So I was wondering, in your MD part where you're tweaking the parameters, have you considered doing Hamiltonian replica exchange, and would it help in some situations? Maybe in some situations not, but where you would have the normal potential and then.
So the idea. So no, the short answer is no. I think it would be useful to do Hamiltonian replicas exchange with something that I didn't speak about, which was scale molecular dynamics. When you scale the value of the potential energy, which is the dual of the parallel tempering, if you want. I think is more efficient. In this case, we are not. Actually, this is a very out of equilibrium description of the bias. So I don't think it would be really easy to use in a Hamiltonian replica exchange, hoping to get some equilibrium. So the nice thing of both approaches is that at some point the bias automatically switches off. So and after that you get a plain MD. So you can straightly collect valuable conformation out of the last part. And then if you have a reasonable path, you can do some approach based on path, and then to like milestoning or other metadynamics or other approaches in order to get the free energy out of them. Please.
Thank you very much. That's a lot of work there in that presentation.
A lot of work to do also.
Too. So quick question regarding the adaptive mesh case. From the image, you see that you have a sort of fine mesh near the charges, for example, right?
Yeah.
What would happen, for example, if you would use, say, a regularized version of the equation where you solve for the reaction potential directly, where that's a lot smoother there. It may be bigger elsewhere, but you might save.
Of course, we are thinking about this, but the point is that it depends how you apply, which kind of regularization you are, which kind of implementation for the regularization. I mean, so of course, the ideal thing will be to be able to remove point charges, but then the sources of your field go on the surface, and figuring out whether bringing these sources to the surface is not just computationally convenient, but doesn't bring some unexpected problem is something that we need to test. But definitely, you are completely right. In the end, we will get rid of we would like to get rid of the grid artifact and provide some, which is grid-based. Some approach is grid-based, but as devoid as possible from artifacts.
Thanks.
Thank you. Maybe this is something for the roundtable, but I'd like to know, what is your opinion? What is the right way to do molecular dynamics in the PP framework? In other words, how we heard a couple of talks about how forces can be computed, but I think it seemed like two alternatives. One was treating the solute and the interior as rigid, and another was computing forces on individual atoms. But then there's a whole question of the induced charge, and so how does that move or evolve in time. So just what are your thoughts and about that?
So the first paper I remember, maybe there were some paper before this, trying to do molecular dynamics on every atom, so on deforming proteins. I think it was from Ray Luo. I'm sorry he's not here. But then the thing I showed that so there are problems. So if you can treat the protein as a rigid body, I think it can be done, and this is something that we are trying to do in the Brownian dynamics approach. When you can afford describing the system as a rigid body interacting from some long distance, I think in this case there are approaches which can be done reasonably well. But if we are talking about an implicit solvent method based on Poisson-Boltzmann, then before the point of before getting to the point of the polarization charge, you have the problem of the fact that the molecular surface area is not continuous with respect to the position of atoms, unless you include some small cavities, but you don't want to put the electric constant of 80 inside a small cavity which may not contain a water molecule. So if you don't do this, then you will get this awkward problem that if you have two nearby atoms, if they are so close that the probe cannot enter, then the molecular surface is doing like this. Then you make a virtual displacement, and the molecular surface does this, and you have instability. And this was already described in that Ray Luo paper, beginning of 2000. I don't remember. So, and this is intrinsic to the description of the surface. It cannot be solved unless we do a modelistic approach to that before the numerical part.